door turned on. There it goes. And I'm going to make the announcement since we are recording, because that doesn't have to be projected. 2 announcements. One immediate, and pay attention to this one. They are going to be testing fire alarms all day today. None of these are drills. None of them are exercises. There's no fire. Hopefully, they're going to be testing the alarm system throughout the building all day long. So don't get up and run out of your classroom, especially this one. Okay. This will be happening all day. If there is a fire, then someone will be following up with fire. It really is a fire, So hopefully that won't happen either. Okay, that's the first one. The second announcement is coming up, not next week, but the following week, is Cougar Connection Week. And I can't remember the exact dates. That would be the 3rd and 17th through 20th. It's Monday through Thursday. Not next week, but the following week. Okay? And there's going to be lots of good, you might say programs, presentations. Both campuses, except for Thursday, they're all on Birmingham campus, but both campuses, very interesting topics, appropriate topics. And there will be, I think, many organizations here. If you choose to do some volunteer work, lots of good things. And you'll see around on the walls, in addition to the Miss Lawson State posters, you'll see the Cougar Connection posters. And they'll list there what's going on when, and also the some of the groups that will be here on campus. Red Cross, I'm not sure if Habitat for Humanity, but lots of places like that you can volunteer. And can I get your name? Ashley, right? Okay. And then there will also be opportunities for you to tie in with some of the campus organizations, like ambassadors, honors college, STEM program, lots of possibilities there as well. So check those out too. And I think they said they're going to try to schedule sometime that week a blood drive. So there's going to be lots going on. And that's not next week, but the following week, Monday through Thursday, both campuses. All right. Let's go on and get set up from the current slide. Okay. Whoa. Okay. Let's see. I think I figured out how to do it here. Let me try this. Do have it plugged in. No, that's not the one. Menu. Okay. Okay. Nothing is oh, maybe I have to point it this way. Okay. There we go. All right. All right. First, any questions on anything we've done so far? All right. We will, knock on wood, finish section 1.4 today. We've been in it long enough. The example 9, I'm pretty sure, is not on the slide set. It is not. So we're going to do it on, sorry, my throat is all froggy this morning. We'll do it on this slide here. Example 9. Let me get my pen set up. Okay. A batter hits a baseball. I think we started this last time, didn't we? A batter hits a baseball at a point 3 feet above the ground at a velocity of 100 feet per second at an angle of 45 degrees. The path of the baseball is given by this function. F of x is equal to negative, nice round number, 0.0032 x squared plus x plus 3. Okay? Rather strange looking formula there. Okay? Where x is the horizontal distance from home plate, and f of x is how high the ball is, the height of the ball at those distances. And of course, when x equals 0, where is the ball? Right at home plate, and that's where he hits it, at 3 feet above the ground. Okay? And then from there, it takes off and goes. Now, the question is, okay, here's the deal. I should have Tyler drawing the picture here because he knows how this happens. And here is Dimitri. If I can find you. There you are. All right. Here is the batter, really ugly batter here. There's the bat, really ugly bat. He has swung it and hit the ball right about 3 feet above the ground. And somewhere way out here, the scale is obviously not the scale, I don't have a big enough. Here, a big enough screen. Here is a 10-foot fence. Okay, this is a 10-foot fence here. And the question is, and that 10-foot fence is 300 feet from home plate. So here's home plate, there's 300 feet, okay, from home plate. Obviously not to scale. The question is, will the ball make it over the fence or not, okay? How in the world would you approach this problem? Remember, the fence is 300 feet from home plate. F of x is how high the ball is at any time. Okay, just to save us here, comes Ron. Okay. They're being very silent. I need some vocal. Okay. What do you plug where?
The base height.
Okay. Here's the equation. X represents what? Say again? Distance from home plate. And what's your 300 feet? The distance from home plate. What is your f of x? Height of the ball. We're looking to see if the ball will be greater than or less than 10 feet at that position. What do we do? Plug in what? 300 for x, because that's the distance from home plate. Okay, so let's do negative 0.0032, 300. It's going to be feet, but they haven't put the other units in, so I'll leave off the units for now. Squared plus 300 plus 3. Okay? Now, negative 0.0032. What is 300 squared? Anybody? And if you got a calculator, you can just plug these in, but say, okay, certainly 9. How many zeros? 4 zeros. You double the number of zeros when you square a number. 90,000. Okay? Plus 300. Well, let's just call it 303. Okay? Keep from having to write that. All right, now we've got to multiply the negative 0.3. Okay, and that's not going to be too bad to do. And here's how I'm going to approach it. Let's take the 0 and move it 1, 2, 3, 4 places to the right. Move this 0 1, 2, 3, 4 places to the left, and we will say it's just 9 times 32. And that's exactly what it is. You don't have to do it that way. Your calculator will take care of it. Well, this makes it easier. 9 times 32 would be 18. 288 plus 303. What? That's a negative 288. Go. Let me see. Here we go. Okay. And what does that give us? Say again? 15 feet. Okay? Now, maybe if Tyler was out there in center field, he can jump and catch it at 15 feet, but the odds are he wouldn't be, okay? So it would have to be home run derby, okay? So, yep, it cleared the fence easily, okay? Any questions on that? All right? There is a checkpoint, as there is after just about every example. Another similar type situation. This is the second baseman throwing a baseball toward first baseman, and you can follow that. And audio-video solutions for the checkpoints are at larsonprecalculus.com. Okay, there is yet another application problem here that's not on the slide set. And let me just go on and erase this one. I'm not going to try to reproduce this one. My baseball batter was ugly enough. This one would take a bit longer to do. But hopefully most of you have your text. And those that don't might want to look on with a neighbor. But I'll try to hold it up so you can see this as well. So what we have here, the number S of fuel stations that sold E85. Anyone know what that stands for? E85. It's gasoline. Say again? 85? No, it's 85. Okay, yeah. If you're in Europe, that might be what it stood for. But this is a type of gasoline. It's 85% gasoline, 15% ethanol. Okay? It's a gasoline ethanol blend. E85 means 85% gasoline, 15% ethanol. In the United States, the number of those fuel stations increased in a linear pattern from 2008 to 2011. Okay? Now, how they represented this in your text is they keep from writing 2008, 2009, 2010. They just put 8, 9, 10. Okay? Understanding those are years. 2008, 9, 10, 11, up to 2015. So from 8 to 11, it followed a fairly good linear slope up here. A good linear fashion. However, after 2011, beginning in 2012, the slope declined a little bit. You know, they had gotten a lot of stations done, so still increasing, but at a different slope. So this function is a piecewise defined function. Now, these are all approximations, but they're pretty close. Okay? Piecewise defined function, and here's what it is. And you don't need to know the graph or the thing. Main thing you need to know is the function. That tells it all. S of t, where t is in years, counting from, I think, t represents the year where t equal 8 corresponds to 2008. So S of t is equal to two different functions. For the first few years, it was 260.8 t, 260.8 t minus 439. Okay? And that was good from years 8 to 11. 8 less than or equal to t less than or equal to 11. And then the second part of that function was 151.2 t plus 714. Okay, and that was good for years 12 to 15. Okay, let me close the door so I won't be bothered. Poor folks across the hall. Poor old guy can't stand, he can't possibly talk as loud as me. So, all right. Now, that function corresponds generally with this graph. You don't need the graph anymore, but you can see what's happening. A fairly steep slope for the first 4 years, a more gentle slope for the next 4. Okay? Now, What are they asking for? Use this function right here, to approximate this isn't exact, approximate the number of stations that sold E85 each year from 2008 to 2015. Do we really want to do every year? No, let's just pick a few years. Pick a year between 2008 and 2015. Any year. 2000 what? Did you say 11? Huh? Okay, someone said 2011. Okay, so on piecewise defined functions, what do you look for first? And by the way, this function has what we call a can't think of the exact term they use. It's a specified domain. It's not free-for-all. It's not all real numbers, okay? It's a, goodness, what is the name for it? They have a name for it that's just a fixed domain. Only 8 to 15. No good before 2008, no good after 2015, okay? Might be sort of good, but this is the only place it's good for. So, 2011 is what I heard. What do we do? How do we determine how many stations were in 2011? Plug it in. What do we plug in where? Second? The top one, exactly, because 11 is included in the top one. So there, for S of 11, which is 2011, that would be 260.8 times 11 minus 439. Okay? And this looks like a good time for calculator time. I'm not about to do that one in my head. I could do a little bit of it, but it would take a while. It really wouldn't take too bad. Let's see. You do it. Say again? 2,000 what? 868. Okay. Where do you think they built the .8 station? Okay. Probably not. Okay. So let's just round that to 2,869. Okay. Because this is an approximate anyway. So we'll just say about 2,869 stations. Or you could say about 2,870 or about 2,900 or close to 3,000. It's just an approximate number. Okay. Let's see what they got in the book. Whoa, not. Did you subtract the 439? No. Oh, let's subtract the 439. Okay. Thought that seemed just a tad high, but... 408? Say again. 430. Okay, I can't hear well. Okay. All right. 2,430. Yes, that's what we got in the book. All right. Pick another year. Second? 2009. We'll do that one. Ooh, we'll get our eraser off of there. Okay. In fact, I think I'll leave the eraser on there. Just change that, and this. Okay. That'll save me some effort. Yes, let's do one of those. Pick one. 13? Okay, we'll do 13. That'll give us the other one. Okay? Where do you go, Waldo? To the bottom, because 13 is between 12 and 15. So we use that one. And you pull out your handy-dandy calculators and calculate away. Oh, no we can't, can we? Because I left up the function for the other one. So let me erase this and that and put in 151.2 and plus 714. Okay, because we're using the bottom piece, I guess you would say. It's piecewise defined. Someone punch it in. What you get? Huh? A little louder. 2680. Okay. Let's see how the book did. 2013. 2680. They got it right. Good for them. Okay, does everybody see how that works? Piecewise defined function. First thing you do, figure out where you are in the domain. Okay? If you're 8 to 11, you use the top one. 12 to 15, you use the bottom one. Okay? Plug in the number to that, and you'll get approximately the number of stations. Ryan. All right. Anyone else come in while I wasn't looking? Okay. Or when I was looking, I forgot to mark it. All right. That enough, or you need to do a few more just to... That enough. Good. Thank you so much. All right. We're moving to the next topic here, which is called a difference quotient. Now, what do those two words mean to you, especially mathematically? Anything? Anything at all? Second? Absolutely. A quotient is an answer to a division problem. How about difference? Answer to a subtraction problem. So this must have something to do with subtracting and dividing. Okay? Brand new topic we've never heard of before, right? Not quite. Well, you may not have heard this term, but you've done it many times in your life. Okay? Mathematical life. Okay? And here's, it tells. One of the basic definitions in calculus, especially differential calculus, differential, difference, catch the connection there, employs a ratio f of x plus h minus f of x divided by h. Okay? Probably looks fairly new, right? No. Okay? What is f of x? This is one thing I told you need to remember in this course. What is f of x? Y. Why not? Okay. So f of x is y. There is a y value, f of x plus a. Well, let's start with f of x. Pick an x, okay, here. F of x will be somewhere up here. If x is your x value, f of x is the y value. Now let's go a little ways over from x, x plus h. A little bit further here, and f of x plus h is up here. So what's that numerator? F of x plus h minus f of x, what would that be? 1y subtracted from another y. Couldn't you call that y2 minus y1? Oh yeah. That sounds familiar, doesn't it? Okay. Now, bottom doesn't look like a difference in x's, does it? But what's your second x there? I'm trapped. Okay. All right, well, I'll use this. What's your second x here? Can you see that? X plus h. All right. Name, please. Oh, Walt. That's right. Okay, I know you're in here. There you are. Okay. Okay. All right, so the second x is x plus h. That'll be our x2. What's our x1? It's just x, right? And what's x plus h minus x? H! And that's exactly your denominator. So what we have here is a y2 minus y1 over an x2 minus x1. And what in the world is that? You've had it before. I'm pretty certain. y2 minus y1 over x2 minus x1. Slope. That's your slope of a line. Okay? That ratio is called a difference, because notice in the numerator a difference. Actually, the denominator is a difference as well, and you're dividing them. Quotient. That's a difference quotient. Now, the key here, h can't be 0, right? Can't ever divide by 0. So you have to move a little ways from that x. You can't be at the same place, otherwise it makes no sense. That ratio is called a difference quotient, and we're going to show that in the next example. Here we have it. Here's your f. f of x is equal to x squared minus 4x plus 7. And they're asking for, find the difference quotient, f of x plus h minus f of x divided by h. What do you have to do first? Before you can find that difference quotient. Plug what in? Second? Okay. Do I see a slip there? Okay, second. Okay. You plug in the x plus h everywhere you see an x. Is that what you're saying? Yes, say yes. Okay, good. That's what he was saying. Okay? Now, so you got to find this first. So let's do f of x. This drives me nuts. All right. Boy, that doesn't look like anything, does it? Okay. Wrong side. There it is. Okay, there we go. F of x plus h. What would that be? You said plug it in. How do we plug it in? Okay. Everywhere you see an x up there, you put an x plus h instead. So that would be x plus h, say again, squared, minus 4 times x plus h, one more, plus 7. That's what f of x plus h is. Everywhere you see the x, you put an x plus h instead. So let's do what it tells us to do. What is x plus h squared? Now there's two ways to do this. One sort of a shortcut, just looking at it, figuring it out. The other one, go over to the side and actually calculate it. What you want to do? Anyone know the shortcut? Okay, if you don't know the shortcut, what would be a way to do that? What does x plus h squared mean? You tell me. By itself, x plus h times x plus h. Okay? Do the math. What does that give you? This is a good old foiling problem, right? First is x squared. Outer is plus xh. Inner is plus xh again. And last is plus h squared. And besides a smiley face, you have the right answer, right? Okay, so what do we do to simplify that? X squared plus 2xh plus h squared. Okay? Now, that should give you a hint on what the shortcut is. The shortcut is square the first number, x squared, twice the product of the two, plus 2 times xh, and square the last number, plus h squared. There's what it is, right there, or the shortcut. Next. Next.
You disturb the 4 negative.
Okay, and what does that give you?
Negative 4h.
Negative 4x.
Negative h.
How about the 4? You said distribute the 4 in.
Yeah.
You left it out, didn't you? It's minus 4h, right? Yeah, okay. I used to be in that too. Never mind. Okay. Next. Plus 7. All right. There's your f of x plus h. Now we're ready to find our difference quotient. The difference quotient is f of x plus h, which is x squared plus 2xh plus h squared minus 4x minus 4h plus 7. Minus, and what do you subtract from that? F of x. Yes, you do f of x. There it is. So I'm going to put it in parentheses so I don't make as many sign errors. That would be minus x squared. Go ahead. Minus 4x plus 7. Okay, there is your f of x. And divide everything by h. There's the quotient part. Let's go up and clear that parentheses. Boy, I'm getting tired of writing this. X squared plus 2xh plus h squared minus 4x minus 4h plus 7. Okay, you clear the parentheses, tell me what to write. Minus x squared plus 4x minus 7 all over h. Okay. Whew. Yes? Okay, a little bit louder.
I'm confused how you got f x plus h.
Okay. Good question. What our difference quotient is f of x plus h minus f of x. So how do we get f of x plus h? Is that the question? Here's your f of x. This tells you, this function tells you, anytime you see an x, or for any value of x, square it, subtract 4 times it, and add 7 to it. Okay? Now we're doing f of x plus h. So we're going to take this and square it, and subtract 4 times it, and add 7, because that's what you're putting instead of the x. Does that make sense? So everywhere you see an x up here, put an x plus h down here, and then do the math. Okay? Good question. That's the key here. And then the f of x, you just subtract it. Now, what can we do with that numerator down below? That big, long, ugly numerator. Say again? Like terms. Okay, you see any other x squareds? Yes, there's x squared minus x squared. Guess what that adds to? 0. So you can just add those to 0. There's no other xh term. There's no other h squared term. But there is another x term. Here it's a minus 4x. Over here it's a plus 4x. Those add to 0. That's nice. There's no more h terms, but there is a constant term. And what's that? Plus 7 minus 7. That adds to 0. So what do we have left? 2hx, don't forget that one, plus h squared minus 4h, and that's it, all divided by h. Now, what do you notice about that numerator? Say again? Yes, it has a common factor of h. So let's factor that out. That's going to be h times 2x plus what? H minus 4. Okay? And we're going to divide that by h. And what do you notice you can do now? You can divide out the h's. H over h is 1. And there's your difference quotient. The difference quotient is 2x plus h minus 4. Okay? Now, I hope that many of you are going to continue in math and get to calculus, right? Yes, good deal. Okay, now, what this is used for is your derivative. And I'm going to give you this is no extra charge. It's not in the scope of this course, but no extra charge for it. I'm going to tell you what the derivative of this, well, okay. What we're going to do is take the limit of this as h is approaching 0. Remember, h can't be 0. That was written on the previous page. But it can approach 0. It can get closer and closer to 0, meaning that x plus h and the x are getting closer and closer together. And what you have, you're measuring the slope of a line, and as that line, the points get closer and closer together, you're getting, rather than the secant line between the 2 points, you're getting closer to the tangent line, the slope of the tangent line. That's exactly what your first derivative gives you. You take a limit as h is approaching 0. Well, what is happening as h is approaching 0 down there? You can actually set it to 0 there because it's not divided anymore. What's that going toward? 2x minus 4, right? As h gets closer to 0, that's getting closer and closer to 2x minus 4. Now, when you take a derivative of this, and you don't need to know this, you're not supposed to know it. 2 times the coefficient, which is 1. 2 times 1 is 2. Drop that by 1. 2x. This exponent is 1. The coefficient is minus 4, so it would be minus 4. Drop that by 1. That's a 0. you get 2x minus 4, which is exactly what you got. Whoa, you've just taken your first derivative. Okay? So, or you've gotten close to it anyway. That's what we use difference quotient for in calculus. Okay? So, you'll see in the text they'll say 2x plus h minus 4, h not equal to 0, but h can get close to 0. That's what we call a limit. Okay, there is another checkpoint there, which has another difference quotient. Please, as soon as you can after you get out of class, do that. Yes?
How come the signs changed when you went from x squared minus 4x plus
Okay. All right. I'm taking it you mean between here and here, right? Is that right? Notice the minus in front of the parentheses. Minus in front of the f of x. That's your f of x minus x. When you distribute the minus, that changes that to a minus, that to a plus, and that to a minus. Just like it did up here, minus 4 times x is minus 4x. Minus 4 times h is minus 4h. Same thing here, it's just minus 1 times x squared is minus x squared. Did that answer it? Good deal. Great questions, by the way. Keep them coming. Okay. Now, so this finishes example. Oh, wait. We did example 11. Let's see how they do it. Okay, sorry. I wouldn't have spent quite that long on it if I remember that they got this one. You start off with f of x plus h minus f of x. Well, you got to plug in what x plus h is to your function f. And that is, just like we did, x plus h squared minus 4 times x plus h plus 7 minus f of x, which you put that in parentheses here just like it was there. X squared minus 4x plus 7. All divided by h. Okay? And where we go next is square that binomial, x squared plus 2xh plus h squared. Distribute the minus 4 in, minus 4x minus 4h. Distribute, and write down the plus 7. And then distribute the minus across the parentheses, minus x squared plus 4x minus 7, all divided by h. Okay? And then you note there are terms that add to 0. The x squares go away, the 4x's go away, and the 7's go away, leaving you simply 2xh minus x, plus x squared minus 4h divided by h. But there you notice you can factor out an h in the numerator, leaving you 2x plus h minus 4. And then the h's cancel out, numerator and denominator, divide away actually, and there is your difference quotient. Remembering h can't be 0, but it can approach 0. It can get very, very close to 0. The closer it gets to 0, the closer that gets to 2x minus 4. Okay. You don't need to know that last part. Okay? They didn't say anything about limits. I just threw that in. All right. Any questions? Does that make sense? Basically same thing we did. Maybe a little neater looking, but not much, right? Right? Okay. Okay. Next. Yeah, everybody got it? Oh, still writing. Okay. All right, everybody got it? Okay. Now, here's a summary, I guess they're saying, of function terminology. Okay? Function is a relation between two variables, we're going to call them, such that for every first variable, independent variable, input variable, part of the domain, all those names mean the same, there corresponds only one output value. Okay? The name of the function, most important thing to remember, y is equal to f of x. Okay? Remember that. Now, it doesn't always have to be x's and y's, but remember, the function is the dependent variable. F is the name of the function, y is the dependent variable, x is the independent variable, and f of x is the value of the function at x. You could plug in a 7 there and evaluate it at 7. You could plug in an x plus h and evaluate it at x plus h. plug in anything you want there. A stick man, that's fine. You can evaluate it anywhere. The domain is of a function is a set of all the possible inputs that can go into that. Remember a couple of problems ago, we only had 8 years were the only things you could input into that piecewise defined function about use of ethanol gas. Okay? That was the only one. That was a explicitly defined domain. That's the word I was looking for. Explicitly defined domain. Okay? Okay, so that's what domain is. The set of all possible inputs. Other times it can be all real numbers. So it's a huge set. Okay. For which the independent variables are defined. If x is in the domain of f, then f is said to be defined to x. If it's not in the domain of f, then f is said to be undefined to x. So 2002 would not have been in that function we did before. It started at 8 and went to 15. 2020 would not have been included. 2018 would not have been included. Okay? So undefined at those values. Okay. But even more importantly, what two types of functions do you have to pay attention to that may introduce some undefined values of x? Two operations. First is any time you're dividing by any expression that contains an x. What do you have to worry about there? Yes, you can never divide by 0. Ever. So you have to pay attention to that. And where is the other place you have to watch out for x's? When they live inside a square root symbol. Okay? Anytime it's an even root, you have to watch out for those two. Because there, you can't take the square root of a negative number. So you can't divide by 0, you can't take the square root. So, if f is defined by algebraic expression and the domain is not specified, then the implied domain consists of all the real numbers for which the expression is defined. And those are the things to look for: variables in denominators and variables inside square roots. All right, or even any even root. Oh, that was the end of the section. Finally, okay. Let's do the vocabulary, top of page 44. Now, some of you don't have this, so listen up. A relation that assigns to each element from a set of inputs or blank. What's the set of inputs? Set of inputs? Domain, okay. Exactly one element in Y, which is a set of outputs or range, is a blank. If it assigns to any value of the input only one output value, what's that called? A function. You got it. Okay. Number 2. For an equation that represents y as a function of x, the set of all values taken on by the blank variable x. What do we call the variable x? July 4th is Independence Day, so that'd be an independent variable, wouldn't it? Okay, never mind. Okay, and the set of all values taken on by the blank variable y, dependent variable y, is the range. Okay, so the independent variable set makes a set of domain. The dependent variable y, that set would be the range. Number 3, if the domain of a function is not given, then the set of values for the independent variable for which the expression is defined is the blank blank. Implied domain. Very good. Okay. Number 4. One of the basic definitions in calculus uses the ratio f of x plus h minus f of x divided by h, as long as h is not equal to 0. That ratio is a blank blank. Difference quotient. Perfect. Okay, homework exercises. I've assigned most of these before, but there'll be a few at the end. Do either 5 or 7. They're both at calcchat.com. 7's at CalcView. Do 9. Do any of the odds 11 through 17. They're all the odds are at calcchat.com. 11's at CalcView. Do any of the odds 19 to 29? All of them are at Calc Chat, 21's at Calc View. Do either 31 or 33 or both. These are all, some of them are piecewise, whatever. Okay. Do any, either of those, they're both at Calc Chat. Then do any of the odds 35 to 41, they're all at Calc Chat. 37's at Calc View. Do either 43 or 45 or both, they're both at Calc Chat. 43's at Calc View. Do either 47 or 49, any of the odds 47 to 55, they're all at Calc Chat. 49's at Calc View. And then some applied problems. You can do any of the odds 57 to, okay, 57 to 71. Now, a couple of these are piecewise defined, some are geometry, some of them are construction, whatever. Pick any of those you're interested in and do any of those odds. They're all at Calc Chat, by the way. Then, this is the new stuff. Some of those were new. Do any of the odds 73 to 79. They're all at Calc Chat. 75's at Calc View. Those are your difference quotients. Okay? And then these get to be, they're fine. You can do either 81 or 83. They're both at Calc Chat. There's some true false, either 85 or 87. They're at Calc Chat. They should be. I really don't care for 89 too much because it's showing you something that's wrong. Okay? But as long as you keep that in mind, you can probably still do it. You can think about doing number 91. That's a think about problem. And 93 is another think about. So you can just think through those if you wish. They get to be a little more esoteric. The others are more like things you'll see on quizzes and tests. Okay, any questions on 1.4? Finally through with 1.4. Okay, so let's move on to 1.5. Okay. All right. You can pick up the rest of it on YouTube. Y'all got a game?
I got it.
Oh.
I got a meeting.
Oh. Okay. Okay. Functions and their graphs, same as before. Chapter 1. 1.5 is analyzing graphs of functions. Okay? What's your name, please? Jalen. Okay. I know you're in here. There you are. Okay. Gain a few, lose a few, whatever. Okay. Glad to have you here. So, analyzing the graphs of functions. All right. Now, the objectives we have in this section, remember 1.4 is pretty long. This looks like it's got quite a few too. Well, the first thing we're going to do is use the vertical line test for functions. If we're looking at graphs of functions, that's the handiest tool to determine whether it's a function or not. We'll find zeros of functions. We kind of did that before. We'll determine intervals on which functions are increasing or decreasing and determine relative maximum and relative minimum values of functions. We'll determine the average rate of change of a function, which sounds like something brand new, and you'll find out it's something we just did. And we'll identify even and odd functions, especially the odd ones, so you have to avoid, okay. So let's start with the graph of a function, okay? Now, we'll study some functions from an algebraic point of view. That's where we're going to spend most of our time. In this section, we'll study functions from a graphical perspective, which is going to tie in with the algebraic view. The graph of a function f is a collection of all the ordered pairs, and what do we used to call ordered pairs? X, Y. What do we call it now? X. What is Y? F of X. Okay, so that's the same thing we did before, except when it was an equation, we called it XY. Now that we're dealing with functions, call it X F of X. Really nothing too new here, okay? Just a named function and how we think about it. Such that X is in the domain of F. And someone said that earlier, X is in the domain, and F of X would represent the values in the range, the dependent values. Okay? Now, I know earlier in your life, sometime mathematically, you graphed equations of lines, right? And probably some other equations too. You put X in and calculated Y's, or put Y's in, calculated X. Same thing here, except it's always X, F of X. Plug in the X, you get the Y. Okay? As you study this section, remember that X is the directed distance from the Y-axis, the horizontal distance from the Y-axis, and Y, or F of X, is the directed distance from the X-axis, or the vertical distance from the X-axis. Okay? And to the right is positive of the Y-axis, to the left is negative. Above the X-axis is positive, below the X-axis is negative. You've done that before, Cartesian coordinate system, okay? So, here is a graph of some function f. We don't know what the function is, but it's the graph of y is equal to f of x, which is the thing to remember. That's what y is. So, for x value -1, there's your y value. F of -1, that would be that. F of 0 would be right up there. Looks like maybe about 1.2, something like that. Over here, x equal 1. It's going to be pretty close to 2, maybe not quite 2. And over here, wherever this is, about x equal 1.3, 1.4, something like that. It looks like the f could be 2 or maybe a little greater than 2. That is your function for any value on the number line here. Infinite number of values here, you can find the corresponding y value. Any value x produces 1 and only one y. Okay? As shown there. Okay? So, that's what we call the graph of f of x. The xy pairs, where the y is your f of x. Make sense? All right, nothing new, just a different way of talking about it. So here's example 1. Use this graph, y is equal to f of x, we don't know what the function is, to find the domain of f. And what does domain mean? Help me. What does domain mean? Set of all the x values that can go into this function. Now, what would you say the domain of that function would be? That graph that you see there. -1 would be the very end one. Now, how do you want to write this? In interval notation or set notation? Say again? Set? Okay. So we'll do it in set notation. Let me get my pen activated. Okay. So the domain of f would be the set of all what values make up the domain? The x values, such that, and what you said, the very first one was going to be -1 is less than or equal to, because why? Because that point at x equal -1, that is a solid dot there, meaning you can have x equal -1. Okay? Less than or equal to x, and then the x will be less than 5. Perfect, folks. Way to go. You see, the 5 is not included because it's an open circle there. Everything close to 5 is, on the left-hand side, 4.999999993 would be okay. 4.999999995, that would be okay, but not 5. Okay? Anything up to, but not including 5. So express this in interval notation. Whoops, long time ago. At least 2 days. Interval notation. What symbol do I start with? Less than or equal to. The what? The bracket. -1, comma. What's it go up to? Up to 5. Does it include 5? No. So what do we put there? Parentheses. Perfect. You did it. Okay? Goes from -1, and counting -1, so you took the bracket, up to 5, but don't count the 5, so you put parentheses. So that would be it in set notation. And anywhere you have an equal with a less than or greater than sign, you put a bracket. Where you don't have the equal with the less than or greater than, you put the parentheses. Okay? We got the domain. Now, let's do the function values f of -1. What does that appear to be? What does f of -1 appear to be? Okay? What does that mean? What are you looking for when you got f of something? What is f of something? Did someone say y? Yes. So what's the y value when x equals -1? 1. Yes, there it is right there. When x is -1, y is 1. You're right. So that would be 1. What is f of 2? -3. Right down there it is. So that would be -3. You see how that works? X, y. F of x is y. So f of 2, that's when x equals 2, would be -3. Perfect. Okay? How about the range of f? What would that be? Okay? The very least is -3. Okay, and what kind of symbol do I put in front of that? A bracket, because that is included, and then it goes up to 3. And another bracket, only this is a closed bracket. Write that in set notation. That'd be the set of all y's. Okay, your range is the y value. Set of all y. Ooh. Okay. Set of all y's such that -3 is less than or equal to y is less than or equal to 3. Oops. Sets you put in braces, not brackets. Okay. All right. There it is. All right. Perfect. Y'all did really, really well. Okay? Any questions on that? Does it make sense? Okay. Let's see how they did it. The closed dot at -1, 1 indicates that when x equals -1, that is in the domain, so therefore you count that in the domain, whereas the open dot at 5, 2 indicates that x equals 5 is not in the domain, but the line went right up to the open circle, so anything less than 5 would be. Anything less than 5 would be. So not in the domain. So the domain is, and they wrote it in interval notation, -1 with a bracket in front of it, up to 5 with parentheses, because the 5 was not included, -1 was. Make sense? Okay. The B one, because -1, 1 is a point on the graph, they showed it to you, it follows that f of -1 is 1, because f of x is y, okay? And -1 was your x, 1 was your y. Got it, okay? Similarly, because 2, -3 is a point on the graph, that f of 2 must be -3. The y values corresponding to x equal 2 would be -3. Perfect. Okay? And finally, because the graph does not extend below f of 2, which is -3, nor does it extend past f of 0, which is 3, the range must be from -3 to 3, inclusive, because both of those points were on the graph. Make sense? Same thing we did, maybe it's a little neater, okay? So the use of the dots, whether they're open or closed at the extreme left and right points of a graph, indicates that the graph does not extend beyond those points, just like we saw before. Now, if, however, your graph looked like this, then that would not have an endpoint, because if it just trails on off into the distance, it means you assume it's going to negative infinity, okay? If it doesn't have a dot at the end. Now, the open circle at the end, you couldn't really draw past that. That would indicate you're missing a value there. You could draw past it, but most of the time we don't. If such dots are not on the graph, just take them off completely, then you always assume negative infinity to positive infinity, if there's no dots at the end. Okay. By definition of a function, at most, one y value corresponds to a given x value. That's what a function is. That means that the graph of a function cannot have two different points on y corresponding to one x, right? Can't happen. So therefore, that leads to a test we can do. Means that a function cannot have two or more different points of the same x coordinate, and no 2 points on the graph of a function can be vertically above and below each other. Follows in the vertical line can intersect the graph of a function at most once. Can't ever intersect more than once for it to be a function. So that observation provides a convenient visual test called the vertical line test for functions. If you have a graph of a function, whether you know what the function is or not, take a look at it. The set of points in a coordinate plane is a graph of a function, y is a function of x, if and only if no vertical line intersects a graph at more than 1 point. None. It can't happen. Okay? Now, and by the way, I forgot to tell you there is a checkpoint underneath example 1. The solution for that is at larsonprecalculus.com. Now, there they gave us the vertical line test, and we have an example, but they didn't do it on the slides, so I have to hold up the book to show you, because not all of you have books. Let's look at this. There's a nice parabola, isn't it? Is that a function? Does that represent a function? No, it doesn't, because there's a bunch of lines, vertical lines, that would intersect more than once. Not a function. Here is a curvy line here going all over the place, up and down, up and down. Is that a function? Yes, it does, because no value, no vertical line will intersect it more than once. Here is a function that's defined only from negative infinity to 0 and from 2 to positive infinity. That vertical line doesn't intersect it at all. Is that a function or not? Yes, it is a function. It doesn't have to intersect, but it can't intersect more than once. So that is also a function. Now, the problem is the domain of the function is not all real numbers, okay? It's a piecewise defined function. Okay. There is another checkpoint at the bottom, and you can do that as well. Okay. Let's at least introduce zeros of a function. Now, what does that even sound like it is? The graph of a function x has an x-intercept at a0, then we say a is a zero of the function. Okay? A would be the x value, 0 would be the y value. And where are y values equal to 0? On the graph. On the x-axis, on the horizontal axis. That's the only place where y is 0. It's positive up here, negative down there, anytime it's there. So that's why anytime it crosses the x-axis, that place that it crosses, the x-intercepts, those are your zeros of the function. So the zeros of function of f are the x values for which y is equal to 0. F of x is equal to 0. So if you have the function, set it equal to 0, solve for x. Those are your zeros of the function. Make sense? Okay. Seems like we've done some of those before. Okay? At least in my head we did. I don't remember for sure. Let's see. Do we have time? Yeah. Let's try to do this one. Find the zeros of at least this a function here. F of x is equal to 3, x squared plus x minus 10. How would we find the zeros of that function? Yes. Just set it equal to 0. 3x squared plus x minus 10. Set it equal to 0. Then your f of x is equal to 0. Those are the places where the function is 0. Where can we go from there? Factor, good word, okay? And we don't know if it can factor. If not, there's another technique we can use. What would that be? If it can't factor, you could use the quadratic formula. Yeah, but let's see if it can factor. What's the, oh, yuck. What's the only possible factorization for 3x squared? 3x times x. Only way you can factor 3x squared. So there's your first. Now we go to the sign of the last term. It's a minus. What does that tell you? One of these has to be plus and one minus. They have to be different. Now, I may have put it in the wrong place. If so, we'll find that out soon. Now, 10. There are several possible factorizations for 10. Name one of them. 5 and 2. So let's try that. Let's do 5 here and 2 there. Okay? Let's see if this works. We don't know. Let's see if it does. You foil it. 3x times x is 3x squared. That works. Let's do the outer. What do you have there? Minus 6x. Let's do the innards, and that gives you plus 5x. And let's do the last. Negative 10. That one works. Is that equal to 0? There's the question. Well, that's nearly not important now. Let's combine like terms. 3x squared. What do you get here? Minus x minus 10. That wasn't the problem. How are we off, though? Only by the sign. So if the sign's wrong, change the signs. Go back here and make that the minus and make this the plus. Okay? And then if you go back and forth, 3x squared still works. Then you have a plus 6x. Then you have a minus 5x. And then you still get a minus 10. And sure enough, that does work to form, well, let's see. Let's see. No, I changed it twice, didn't I? Sorry about that. Yeah. That gives you the correct answer. Okay? So, now that we know that's the correct answer, okay, I'm going to take off my, whoa, I thought I was going to, but it won't do it. Come on, there we go. Okay, take off my construction lines there, and where do we go from there? Okay? We know that that equation is true. 3x minus 5 times x plus 2 is equal to 0. How do we find the zeros of the functions? Set each of them equal to 0. So either 3x minus 5 is equal to 0, or x plus 2 is equal to 0. That's the only way you can get two entities to multiply together, give you 0. One of them has to be 0. Okay? So what does that first one give us? Say again? Yeah. Add 5 to both sides, and that gives us 3x is equal to 5, and then divide by 3, and that gives us x equal 5/3, one of our favorite fractions, right? Or, yes, yeah, x equal negative 2. Subtract 2 from both sides, and that gives you x equal negative 2. There's the two zeros of the function. Okay? How do you check? Plug them in, plug them in. And let's make sure. Well, this takes a little bit of effort on the first one. What is 5/3 squared? 25 ninths. And if you do 3 into 9, it would be 25/3, right? So you got 25/3 here, plus 5/3. That would be 30/3. What is 30/3? 10. Minus 10 is 0. So sure enough, that's 1. Let's plug in a minus 2. Minus 2 squared is 4. 3 times 4 is 12. Minus 2 is 10. Minus 10 is 0. Yes, those are your 2 and only 2 zeros. Good deal. Let me give you a few homework exercises here. I knew you wanted some. Okay, so don't leave without them. You can do either 7 or 9. They're both at calcchat.com. Calc number 9's at CalcView. Do either 11 or 13. They're both at CalcChat. 11's at CalcView. And then start doing some of the odds, 15 to 25. If you can't do them all, hang on. We will do the rest next time. All the answers are at CalcChat. Okay? So, we'll pick up there next time with example 3B. We got 3A done. We'll start with 3B. Good deal. Have a good weekend. Seems like no time it passed since I said that before. All right. Good deal.